So the subject audit enhancement module moves on from where we were last year to put a bit more theory in and develop sort of AS level maths. So I'm going to talk about what is involved in this module and your assignment. We'll talk a bit about the purpose of maths education, and then we're going to look at cubics and circles if possible. Now what's happened this year is you've got a reduced number of webinars, but they are now 3 hours. So they were 2.5 hours last year. They're now 3 hours, but so I've had to kind of rejig how I did things, and what it's meant is there's kind of a bit, we're missing a webinar, we've got a bit more in each thing, so we'll see how much we get done. So webinars are going to be 9:15 to 12:15, and we just only have 4 with you. So I have 4 webinars with you, and I'll see you in February for a day and a half rather than just a day. So this is just the the general aim, but basically by the end of this module you should be able to articulate a kind of subject knowledge, analyse classroom practice, and understand the relationship between subject knowledge and pedagogical decisions. And we will be a development of deep and profound understanding of maths. I mean, it's not going to be everything you can possibly do, but take it a bit further. We're going to be doing smart maths activities and exploring different perspectives on nature of maths and good ideas and that kind of thing. Here, this links, oh, it doesn't work. Why does it not work? This is supposed to link to the spreadsheet, which is your plan for this year, so you can see, and hopefully this should, have you been sent anything like a new handbook or anything to show the timetable? Hopefully you have received something. Well, you must have, otherwise you wouldn't have known what was going on. So here we are today, 23rd of September for the first webinar. You've then got a self-study next week, which has got questions based on this, which I think I've already put on Blackboard, but if not, I'll do that after this. And then I talk to you again on the 14th of October, and we'll be doing calculus, and following that in December. So then there's nothing until December when you have a self-study on that. But I can put the self-study up before, obviously. I'll just put it up at the same time, so you can do that whenever. So that's all we've got this term. Then next term, in January, I have a webinar with you. And at the beginning of February, so we've got 2 webinars. And then that is it for webinars. Because I then see you in that intensive study week that's in February, just after the week after half term. And what we're doing is I'll have a Monday afternoon session with both you and Cohort 4. So I'm going to do decision maths so that we can do a topic that we can all do together. And then I have you for the day, and we'll be doing trig and some mechanics. And that's it. So it's based on the fact that the feedback was they wanted more face-to-face rather than so many webinars. So that's it really. So it seems a bit short. And then after I see you in February, that is the last time I'll see you, I think. So your assignment is due that week. I've got the dates the wrong way around there. That should be the 29th as well, maybe. I think actually maybe this should be. So it looks like it's before the ISW. So basically by the end of the February half term, you need to submit your assignment. And then you come on the study week feeling like you're free. So that's the idea for that. So going back to this. So yeah, that's the learning outcomes. Demonstrate depth, systematic understanding of key ideas in maths. Analyse and critically reflect on the impact of your subject knowledge on pedagogy. Critically engage with and analyse the relationship between theory, policy and practice. So that's kind of the step up. It's not so much just about, oh look, this is me and where I've learned stuff and let's bring in some theory. What you're going to be doing on your assignment for this one is taking an area that you're interested in, analysing everything around it, and then doing something in response to that in practice. So your assignment is due, as I've said, on the 27th of February. They have not clarified to me yet if this will stay the same. It was something that they were meant to do, which I need to chase up, because Carol has now left. I think whoever was taking over wanted to actually have a look at what she'd put. So this is last year's, but I'm sure it will follow a similar sort of theme. So the idea is that you do a 15-minute presentation to some of your colleagues at school about whatever topic it is you're going to choose. So what you submit to me is your written presentation. So if you write out what you're going to say with all the theory and the references in it, it's a bit of a weird, it's kind of like you write a slightly informal essay that you can then present to them for 15 minutes. Now it turns out that 15 minutes of talking is about 3,000 words. But what you say will be equivalent to 3,000 words. It's less important as long as it keeps the time. And what you're going to do is you upload the slides from your presentation, those notes that you've made in order to talk, and then they fill in, your colleagues fill in some feedback, and you upload those feedback forms as well. I think you need to scan them in or something like that. So that's all uploaded to Turnitin, and that's what I look at in order to mark it. Now, what we've been able to do before, this is subject to change, is you select one topic within your subject area that you've explored or you're going to explore. So it could be how do you, best way to teach maths to people with a particular special need, how do you reach girls, how do you manage, the thing is it's got to be kind of specific to maths. So the behaviour management thing is tricky because it's got to be kind of within maths. Or you can choose up to 3 activities or resources. You don't have to choose 3, it's up to. What happened in the first year was some people went down the activities route and they, basically looked into the theory and chose something based on a particular theory of what they were trying to achieve, used that resource, and then critically analysed how it had gone, which is great, but actually when you do that 3 times it was too much. They overran and they had too much to say. And actually they were doing the same sort of thing as the people who chosen one topic, but they just couldn't quite get the depth, really. So just be wary of that. But, there might be something that you're really, that jumps out to you right away, that you're like, oh, I'm really into growth mindset. So last year, when a cohort 2 was really into growth mindset, so he looked at how he could embed that within his maths teaching. And another, I can't remember what he did, but he chose a topic. It was something like teaching negative numbers. And he really researched the different ways that people have taught that before and the issues that kids have. And he wrote about where, or talked about, I suppose, virtually it was written, how he delivered it and what had happened and analysed, that. So that's kind of what you need to be thinking about. You need to be thinking about, is there something, or what is it that I'm particularly keen on, and a little sort of something that I could demonstrate in class. Part of the assessment guidance was that you needed to show pupil progress, as you do generally now, have demonstrate pupil progress. So this was kind of breaking it down a bit more. No, I haven't written that, but oh yeah, here you go. Comment on and critically explore the topic in your own practice in supporting pupil progress. So that's the key. I think when I was marking it, I was looking for hitting those particular things. You know, have you talked about how it's affected pupil progress? Have you actually done something in practice? And is that practice, the reason you've chosen that, is it backed up by theory? And is it then critically analysed? So that's what you need to be thinking about. I will chase Brighton up because what I've put on here is the old guidance, and I need to check whether they're planning to change it in any way. But I will talk to you on the 14th of October, and unless you're really keen beans, I think that's probably sufficient. Anyway, so moving on. Any questions about any of that? Okay. So a bit of theory. When you were at school, why did you think you were learning maths? Anyone want to volunteer an answer?
It's just one of these things that you never really knew. It's because you were learning maths because they had to do something to employ maths teachers. That was kind of it. You never got any real explanation of why you were doing it, to be honest with you. I know it's like the numeracy side you could almost understand.
Yeah.
I can understand more about learning the numeracy side now, but at the time, it was like, no, it's just stuff. It was all just numbers and calculations and no real explanation of what it all meant or where it all fitted into stuff, and very rarely put into any kind of real context that I remember anyway.
Did that bother you?
I didn't know any different.
No, well, exactly. I don't think I ever even thought about it. So why do you think we teach maths? Now, why do you think we teach maths?
It's now more about, it's a mixture, isn't it? It's always, I mean, you teach maths, depending on what you want to use it for. I mean, you can, especially, it almost seems like that when you actually look at the new syllabus for the new GCSE, if you're going in from the foundation side, that's generally looking at developing more numeracy skills that you can use to logically think through real life problems and use it to critically analyse stuff, but look at it from a mathematical perspective. Whereas when you get into some of the higher skills, it's more about almost like a warm-up, getting you ready to take you to the really further maths, like in your A levels and beyond from there. But it's all about using those number skills, A, to generally get on in life, but also to know to analyse what is happening in life. Is there patterns behind something? Are there links between something? Does one particular thing correlate with another? That's how I appreciate it now, is then just trying to figure out how to get that across when you're teaching the other skills and to the actual kids now, really.
So have a think now, just quickly write down, if maths education could be anything you want it to be, write down now, if you write something down about if it could be anything, what would you want it to be? I'll just give you a minute or so and then I'll get you to read those out. Hugh, what have you written? You're muted. You've muted yourself, hello, or have I muted you?
Oh, sorry, I had a thing hovering over it and I must have pressed the click button.
Have you written something
Yeah,
down?
for me, yeah, I've written down a couple of notes, but I've actually been thinking about this because I've been saying it to the boys.
Oh, yeah.
For me, they need to learn math because it's a foundation for everything. If you think even poetry, it's got a mathematical formula to it. If you look at football, it's all maths. You look at carpentry, driving, everything in the world is to do with maths. And the better you understand it at an earlier age, the easier your life will be when you're older. When I'm using a example with the older, it's a bit of a teaser to show them that if they know the math, they'll get something out of it. It's I just put up a bit on the board. Would you rather have £1 million in your bank today or a penny in the bank which doubles every day for 30 days? And 9 times out of 10 they'll go for the £1 million. Then you get the boy that works it out and they come out something like 9.7 million greater. And I just go to emphasise that you can't take shortcuts with math. You need to put in the work to find out what you're going to get rather than just taking what looks like the easy option.
Yeah.
So by teaching kids the importance of doing the math and focusing, they will get more out of life rather than just taking the quick and easy, everyone will do it for me. So that's just my thoughts on it.
Good. And Mark, what do you put?
Life put along the lines of math education ideally needs to be focused on real life situations, exploring why things work and how things interrelate. You know, so it is literally like, you know, I was doing this thing with, you know, I said earlier that I was doing estimated means from grouped averages and what have you. We were doing these exercises yesterday where we were getting 2 tables of data, estimating the mean for both, and then the question in the book basically says compare, and like, you know, the kids are just coming up with the whole one is greater than the other, which means so-and-so travels further. And I said, right, okay, why? Why do they travel further? What makes, you know, what does it say about, because it basically was comparing teachers and office workers, and office workers travel further. And I said, well, why do they travel further? And they went, because they get paid more. Well, it could be. What else? It's a better job. Teachers live nearer to home. Office workers work further away. And they started to actually think of reasons why this would actually be. And that's more kind of what we need to be pushing, is like idea of like this whole number sense thing and the ability to think beyond just what is actually written down in front of you. It's not just a calculation. It's why is that calculation coming out like it is, and that's really. But you know, at my particular school, trying to get kids to reason like that is just, you know, like, yeah, just give me the sum, sir. That's all I want, and that's if they even want to bother.
Yeah, and that's always been the problem. Reasoning has been one of the fundamental purposes of math education. Developing reasoning abilities. But it's so difficult, isn't it? Because these things come with maturity, and we need to try. Yeah, you're right. As Hugh said, you want to try and get them as young as possible, so they mature quicker and get this sooner.
Yeah.
Because otherwise, but it's interesting. So both of yours, and it's probably, I suppose, because of your backgrounds, because you've come from real life applications of this, are more about the practical reasons for it. So these were by someone called Ernest. That's his surname. He thought there were 5 competing views. I'm sure there's sort of actually subsets of these and various different ones now. But there was the industrial trainers who want you to acquire the basic math skills and numeracy and kind of social trading and obedience. And I think there was a lot of that. There still is in the lower level, you know, definitely sort of in lots of the level 1 qualifications. You feel that, you know, that you just desperately need them to achieve this at least. The technological pragmatists to solve practical problems with maths and IT. I think you guys probably are fitting a bit more into there. I'm a bit more here. I'm a bit more of a purist at understand and work with advanced maths, gain appreciation. You know, happy. Well, no, I'm probably somewhere in between those two. Sort of, I love maths for the sake of it, and always did do, and actually really didn't care about the applications of it. But in terms of obviously teaching and attracting kids into it, and obviously creating members of society that are useful, I sort of see some stuff in between those two. Progressive humanists, they want children to gain confidence, creativity, self-expression through maths. It's a bit hippie, but you know, I thought that, you know, that's, I would say sort of the person that I observed is a bit more like that, in that she was just like, well, yes, you just give them open-ended tasks, and they develop, and actually she always had high exam results because she's just left them to play. Well, they're not really, she's very experienced at it, obviously, so she's able to guide them appropriately. But they are engaged and they're choosing to take part in her lessons. And I think we're probably all public educators. I mean, that's what we are, aren't we? Empower learning to be critical and mathematically literate citizens of society. So maybe perhaps that is the most important one. But sort of in terms of how you then act as a teacher can obviously be very much dependent on that. The industrial pragmatists, they are the ones who stand up at the board. They say, this is how you do it, now do it 100 times and get on with it. Purists, more, you know, here's the knowledge and precision, very traditional lecturing sort of type. I'm probably not there either. Progressive is where you just leave them to be, really, doing open-ended tasks. And the public educators encouraging students to discuss problems, makes them more relevant to their lives. So, what do you guys think? Do you think you're here or public educators?
Yeah, a mixture between that and possibly the industrial pragmatist, to be honest with you.
Yeah, and I think that looking at them all, there'll be a bit of everything, isn't there, depending on what it is that you're doing. And where in the year it is, and all those sorts of things. You know how at the beginning of the year you keep it a bit more close. Well, I do. You sort of, you know, because you can't just let them be free right away. You need to kind of measure where it is that how much they can take from you talking and all that. What do you think, Hugh?
I'm not 100% sure. I mean, some lessons I'm like progressive, some lessons I'm purist. Just sort of like goes all over the place. All depends on the situation and the class in the day.
Yeah, it does. I think there are some people who are definitely go down a particular route and that's all they do. And I suppose that's probably where the problem, you know, that's when, I don't know. I guess then the kids know what they're getting, you know. I think what happens is if you have a progressive teacher who does everything by learning through inquiry, or you have one who only lectures the whole time, if you are someone who learns by listening in that way, then you're probably delighted, and it's only if you don't that you're in the wrong class. But I mean, that's why we do a mixed thing, isn't it? So that we can hopefully do that. Anyway, so there's just a bit of theory and a bit of further reading there about why we teach maths and that sort of thing. Right, let us get on to some maths. So I asked you to, well, in the announcement, hopefully you saw, to have a bit of a practice of some of your quadratic stuff, because cubic is basically made up of a quadratic and a linear smushed together. Well, I don't think I've ever said that before. That's really good. It's a cubic has an x cubed in it, and in AS level, we sort of progress by reminding the students about straight line graphs and quadratic graphs, and then progress into cubics. They have to be able to manipulate them algebraically as well as sketching them. Here we go. So what we're going to look at today is the factor and remainder theorem. That helps us to basically identify the roots of a cubic, carry out algebraic division, which I will try to do via webinar, which might be quite tricky. And then the same goes with U division. And because use relations for the symmetric functions for roots and the equation of the coefficients. Use relations for the symmetric functions of the roots and the coefficients. I was not planning on doing this actually, so you can ignore that. I must delete that. I don't think you can possibly get that done. So that's actually, that uses a bit of an equation which I didn't make sense to do. However, quadratics we are familiar with, hopefully. A cubic polynomial has an x cubed term, a quartic has an x4, quintic x to the 5, and so on. So polynomials, there's nothing being divided, it's just a order form, ax to m's, terms, stuff like that. To expand a cubic, when we have a quadratic, we can factorise it into 2 brackets. So when we have a cubic, we can factorise it into 3 brackets, because if you think about how we expand things, we'll get an x times an x times an x gives us our x cubed. And then we have to fix the other bits to get the cubic. Now, with a quadratic, we can use inspection, where we look for 2 numbers that multiply together and then 2 numbers that add to make those bits. So you can just kind of look at it. That is pretty difficult to do with a cubic. I would be amazed if you could do that with a cubic straight away. We will do a bit of that, but to go straight to 2 brackets, 3 brackets would be quite amazing. So we'll get to factorising. Let's start with the opposite, expanding. To expand this, rather than trying to do x times x times x and x times, rather than doing all 3 brackets at once, that would be too much. Some of the kids do try to do it, and then they just lost themselves. So we choose 2 of the brackets and do those first. It doesn't matter which ones. Then we do the other bit. So we're going to leave this bit as it is and just expand the quadratic. So when we expand this quadratic, what do we get? When we multiply these 2 brackets together.
X squared minus 3x minus 10.
Yeah. Excellent. Now that we've done that, then we can go along multiplying in the other one. And it totally depends on your preference, whether you prefer to work along this bracket, multiplying each bit by the first one, and then multiplying all of them by the second one, or the opposite way around, so you go x squared times x squared times 1, 3x times x, 3x times 1. So this one is done all of those by x, and then all of those by 1. And actually that's quite a nice way. I have seen it done like this, because then you can line it up underneath, you see? And then just add those together to get x cubed minus 2 squared minus 13x minus 10. Have you done that before?
No, first time I've even seen it.
Okay. Hugh, have you done this before?
Yeah, that's back in college. If I remember the way I used to do it.
Yeah, I don't think I do it like this, but it's quite nice now that I see it. So I'm hoping that I think I've got one for you guys to do. There you go. So have a go at doing this one yourselves. So expand the 2 brackets and then just multiply everything that you've got in your quadratic with this bracket at the end. Okay.
See you later.
So put your hand up when you've done that. Oh, sorry. I'm just on a webinar. I'll call you this afternoon. Bye. Right, excellent. So, if you expanded out the first two, then you should have got x squared plus 2x minus 3. So when you multiply all of that along, then again they've got all by x and all by minus 2. Hopefully, have you got, so these two cancel out? No. X cubed minus 7x plus 6? Is that yes or no?
I didn't to start with. I went through it because what I actually did, I saw the negative one. Thought, you know what, I'm gonna make this easy for myself, and actually did the x plus 3 times x minus 2
Okay.
to find the quadratic, and then did the x minus 1 afterwards. And then just so I've done it, I thought I've done this now, and then spotted that I'd missed the trick with the negative 1. I called it just for the last part, and I got plus 6 rather than minus 6. But I hadn't applied that for the x squared and the 1x. So I went back and then redid it and got like the x cubed 7x plus 6.
Okay. I
got there, but it took me a second. I realised that I'd gone the wrong way at one point. But
well, it's so good that you realise. I mean, I think this is one of those things that students don't always take the greatest care over, because it's, you know, they're like, oh yeah, this is nice, something nice and easy that I can do. And it's just, you know, especially with the signs, it's so easy just to lose track of where you are. Is that all right, Hugh?
Yeah, that's what I got. Double check my work.
Good. Right, so having been given this though, trying to knowing the note with that would be fairly tricky. So we have the factor theorem, which is all about how can we factorize this. So this is the graph of this function here, x cubed minus 6x squared minus x plus 30. What do you know about, I say it's solution, this is not a solution, isn't it? I should say that this equals 0. What do you know about that solution, or what can you tell me about this graph?
well, if that's the case, then you're going to have 3 parts to that when it's factored.
Yeah.
So if that equals 0, then basically the 3 numbers that you're looking for are going to be where the graph crosses the 0 line.
Right. Well, I think that's minus 2, 3, and 5. So those are the roots. Yeah. Those are the roots of the equation.
Each of those can, yeah, because you can find the minus 6x with that, and you can easily find the plus 30 with that, can't you?
Right. So that's the thing. If this is a 30, you're right. If we think about, going back to this, if we think about this, we get that 6 by multiplying all these things together. So that means we know that we're looking for factors of 30. The roots have got to be factors of 30. So yeah, it has 3 distinct solutions, as you said, which is when y is 0. So if we can find values for x which make the equation equal to 0, because we're talking about when this equals 0, if we could put numbers in here and get it equal to 0, we would know we had the right value of x, wouldn't we? So, for example, if I put 3 in, 3 cubed is 27, 3 squared is 9, times 6 is 54, so 27 minus 54 is minus 27. minus 3 is minus 30, plus 30 equals 0. So, yeah, so what's great is that in the exams sometimes when the kids forget completely about anything, often they just try numbers and they just shove numbers in. And then they're like, yay, it worked, it got 0. I know that 3 is one of the answers, yay. Now, the idea behind the factor theorem is that you do that once and you find one factor using trial and error. However, once you've found one, you're not expected to find all the others by trial and error. It has to be said, because I mark add maths and it has this in it, if they have gone through and tried all the factors and found the 3 roots, then they've got the answer and I give it to them. But you're supposed to find the first one by trial and error and then use inspection or long division to find the others, rather than just basically using trial and error. So we know there must be factors of 30. Generally, when we advise students to do it, we start by thinking about 1 and minus 1. But, you know, it might take a while to get there. Anyway, so what we know is that we can represent the roots that we put in here in brackets as a factorized cubic. Now, what do you notice? And if you think back to quadratics, and when they're factorized, so if I had this, this is my quadratic, what could you tell me about the roots? What are the roots?
In what way? You're trying to get the fact that if you multiply like the -2 and the +3, that you're going to end up with a -6. Is that what you're getting at? Or?
No, I mean if this was a function written in factorized form.
Yeah.
What would the roots of the graph be?
Oh, -2 and +3.
Is it? I mean, this is a trick question. I'm asking you basically.
Oh, hang on, no. Would it be the other way around?
What are the steps we go to once we've got to this stage of factorizing? What do we do when we then solve it?
Ah, it's the other way around, isn't it? So one's going to be +2 and the other one's going to be -3, because that's what you need to be able to put in to get it to 0 in the first place.
Exactly. And I think that's what you need to make clear to the kids. What value, so this is what's happening, basically x minus 2 equals 0. So what value needs to go in here to make that true? And it's 2, isn't it? So, so that is the crux of the factor theorem, which causes confusion. The difference between factors and roots, and this fact that when it's factorized, the number in the bracket, I mean the number's correct, but the sign, it will be the opposite sign. So yes, they do get a bit confused about that, and that's true. Sorry, go on.
So, sorry, I was just thinking when we were looking through this, because we're obviously trying to find the 3 roots, and you know, obviously your factors of 30, because the only reason I'm thinking of it, because I've just been doing prime factorization with the kids.
Yeah.
Could you actually prime number factorization to try and give you, rather than literally just doing trial and error, you could like do a prime factorization of 30, and your combinations thereof. I mean, as it turns out, there's only 3 prime factors, so that's actually going to give you your factors straight off.
It doesn't necessarily have to be prime though, because you could just have 6 and 5 and 1. You know, it
Oh, right, yeah.
could be that to get 30. It's not necessarily prime. But, I mean, generally, I mean, the questions that they're given, 30 would be the biggest, probably. So you're looking at 1 minus 1, 2 minus 2, 3 minus 3, 5 minus 5, and 6 minus 6, 10 minus 10. I mean, this is a lot. Normally they don't choose something that has more than about 6. 15 and minus 15. So rather than bothering to look at all the combinations of it, because of the way these match up, obviously with sort of each other, you're likely to only have to try sort of those ones before you get one. So that's why, but that is why we say don't just do it by trial and error, trying them all. You find one, and then we do what we're going to show you next. So you find one, and then we find the quadratic that's left. Oh, sorry, this is just going through all of what I was just saying, having got a slide about it instead of having to interrupt myself, but never mind. So this is just saying, when we factorise, as I was just saying, we have these two brackets, but the zeros of the function, the roots themselves are x equals 1 and x equals minus 3. But these are the factors, and they say to them, write down the factors. They mean the bracket x minus 1. That's the whole factor. That's the bit that divides into this. The root, they call them zeros here, but we tend to call them roots, are the number that is basically written on the x-axis. So x equals 1, x equals minus 3 in this case. So when we are doing the factor theorem, what we do is we put the root that we think, because that's the value of x in, and substitute it in, check that we get 0, yes, that is a root. But the factor, if we do that, is x minus 1. So when we've been through this process from the opposite direction, so we haven't known the brackets yet, we do this through trial and error, then, as it says, reversing this process enables us to factorise them, because here is a cubic. Let's try x is minus 1. So this is us basically using the factor theorem, because what we do is we put minus 1 in, work all of that out. We've got 0. Excellent. So we know one of the roots is minus 1. And if I know that one of the roots is minus 1, that means that x plus 1 is the factor. So that is the key takeaway. That is the factor theorem. That is the bit that confuses the students. So they put in minus 1. So then they think, oh, excellent, my factor is x minus 1. And so when they then factorise it, they've actually written everything down back to front. Were they to multiply it out and check, they'd realise that they hadn't got the cubic they started with, but oftentimes is short. So yes, the key thing is this change of sign. So this is the factor theorem. This says if f of some number gives us 0, then the factor is x minus that number. So it changes the sign. Is that all right?
Yeah.
Yeah, so that's the key thing. And in fact, you know, something that I don't ever go back and do, but you can apply this to quadratics, this factor theorem. So rather than that whole complicated, oh, okay, I need 2 numbers that multiply to do this, and 2 numbers that add to do this, they could just do this, putting numbers in a trial and error fashion. So if you've got a class that really, really struggles with factorising, you can always bring in this sort of like realisation that, look, when we're doing this multiply 2 numbers to make the last number, this is what we're really doing. So using the S in a sort of more basic way, because actually it's more basic than factorising, just by looking at it. So what we do to factorise the whole of a cubic is we start by finding the linear factor, and that's what we've been doing. So when we try f of 1, which is generally we start with 1, we'll try f of 1, we'll pop it into here. Yay, that one worked straight away. So f of 1 worked, so what is my linear factor?
-1.
X.
X minus 1.
Yeah, x minus 1, that whole thing is the factor. So
yeah.
we now know that that is one of the brackets. X minus 1 is one of the factors. So now that we've got that one, we can figure out what is the other bit that's left, and it will be a quadratic, because a linear times quadratic gives us cubic. That quadratic, remember, may not factorise, so we may just be left with a linear and a quadratic, or we may be able to factorise the quadratic as well, so it's 3 brackets. So, to factorise this fully, I want you guys to do a bit of trial and error first, see if you can figure out one of the factors. Actually, I think I've got one of these for you to do in a minute. So maybe I will just do this one first, actually. Unless anyone's copied one. If we have 1, 1, minus 2, 5, okay. No, it feels like we want a minus, doesn't it? Then, so we know it's got to be the factors of 8. So those are our options. I think 1 doesn't work, doesn't it? 1 gives us 12, but because these numbers, you can see that those make 8. So we kind of just want them negative. We try the negative one. As you said, that could be a factor. We try the negative one. Yay, that works. So x plus 1 is a factor. So this cubic can be written as x plus 1 multiplied by the quadratic factor. So there are 2 ways to figure out this quadratic factor. My preference is long division, but a lot of people hate that. So I will do the other way first, which is inspection, which is basically just thinking about it and figuring out what it could be. So we know that we've got an x plus 1 bracket. We want to know what's in this bracket. We just compare what's going on with what's going on over here. Now, you could write in a generic quadratic here, like ax squared plus bx plus c, multiply it all out, and just compare the coefficients. That is basically what we're going to be doing, but kind of in a trying to do it without having to do all that way. My brain does not work very well this way. But a lot of people go, why on earth you spend all that time doing long division when you can just look at it and work it out? So we'd be doing x times something x squared must be giving us our x cubed. So because we've just got a plain x cubed, what do I know about the coefficient of my ax squared?
It's just going to be x squared.
Yeah, exactly. It's just going to be x squared. Yeah, so we get the x cubed by just putting in an x squared there. And equally, at the other end here, the number 8, we've got 1 times something is going to give us 8. So what must that be?
It's got to be the 8, isn't it?
Yeah, so we know right away those 2 bits, and then all we've got to worry about is the one in the middle. Now, the only tricky thing in the middle of a quadratic is obviously it's actually made up of 2 bits. So when we're trying to figure out how to get, so if we start with the first bit and think, okay, to get the x squared, I'm going to have this bit times, this bit times this bit, so a 1x squared, and I need this times something. So I've got a 1x squared plus something, which I will call b at the moment, to get my minus 2x. Oops. That's right, isn't it? That'll be that times that, yeah. So what will bx squared be?
X squared. It's going to have to be negative 3x, isn't it?
Here it is. Yeah. So you can then check that for the other one. So that's going to give us, yeah, 1x squared minus 3x squared gives us the minus 2x squared. If we just check that against the other one, we get minus 3x plus 8x. Great. That gives us our 5x. And that is it. So we have to do minus 3x. So yeah, putting it in already. So that's just then, that's just then underneath checking it all out, and you can check it by the time. So there we go. It is just a case of comparing what's going on with that bit. I just find that I can't just look at it and go, oh, to get that, I've got a 1 in that. That's why I wrote down that little thing with the bx. I have to write that bit down to see it. But a lot of my students are like, what are you doing? Just look at it and write it in. So just depends on how your brain works. Then we check whether this factorizes. This one actually doesn't factorize, but you'd just be factorizing it like you always do. So that is in fact the whole of it. Does that make sense? Any questions about that?
Yeah.
Have you used that way before?
Yeah, that's the way I used to do it.
Right. And I think it's totally down to personal preference. I always taught long division as the method of doing it because long division used to be a separate thing that they had to know anyway. So I thought, well, if they have to know it anyway, then they may as well do it in order to use it to find out what to do. So this is not so much long division. This is more simplistic division. Sorry, Hugh, can you mute me again? No, mute you actually. Sorry, I don't mute you. If we want to divide, so this is now a bit of a jump. You know, you can attempt to teach the kids how to do long division using numbers and relate it to algebra. I tried that once in my whole career, and it went down like a lead balloon because basically the kids were struggling with the numerical long division. And so then they were like, oh, we hate this, oh, we hate algebra when we have to do long division. So I was like, forget that, forget about the numerical long division, because they basically couldn't. The problem was that they had already forgotten about the numerical long division and couldn't do it, so they then struggled with this. But ultimately they're saying, if I divide 2x plus 6 by x minus 1, the thing you've got to say to yourself is, well, how many x's are in 2x? So there's my sort of bus stop thing. So first of all, you're going, well, in order to divide this in, I have to say, how many x's are there in 2x? So 2x over x is just going to be 2. So x into 2x is just 2, and we write that above the number. Okay, they haven't there, but I tend to write it above whichever one is the same sort of term. Then you multiply that by the x minus 1. I mean, this is how long division works. You then multiply by that, and you take it away to see what's left. So that's what we then do. 2 times the x minus 1 gives us 2x minus 2, and we write that below there. Then we take away this number as such, take away that one, so this one minus that one. And we're left with, in this case, 6 minus 2 is 8. So when you divide 2x plus 6 by x minus 1, then basically that goes in twice. As you could see straight away, can you? 2x minus 2 would be fine. But you've got 8 extra bits. So that's your remainder. And actually, in terms of what that actually is as a fraction, it's 8 over x minus 1 bits. You've got 2 plus that bit when you divide by that. Now, more often than not, if they're doing a long division at AS, they're not going to end up with a remainder. They're going to work through the long division in order to basically get the quadratic factor on the top. So they'll divide by the linear factor and be left with the quadratic factor on the top, like this. Oh no, sorry. Because I talked about remainders here, I was then going to just make a bit of a segue into the remainder theorem. The remainder theorem goes with... Sorry, I muted myself, I was stupid. Yes, I was just going to make a segue into the remainder theorem because it is basically the same as the factor theorem, except the factor theorem works when you're trying to find the factors of the equation when it's equal to 0. If it is not something that divides exactly, what will happen is the factor theorem will give you what the remainder is. So, if we want to know the remainder of this, when it's divided by x minus 1, if I've got x minus 1, what do I need to put in here? This is the reverse of what we were doing. You know how we put in a number and we got the factor and it was the opposite sign? This is now going back the other way. If it's divided by this, then we replace x with 1. So plus 1.
So if you put the x plus 1 in, it's actually going to give you the root, isn't it?
Yeah, so it's the opposite. So that would, if this was the factor theorem, and we were told that x minus 1 was a factor, then when we put this in, the 1 would be the root, and we'd know that because it would equal 0. Now in this case, it doesn't equal 0, which means that x minus 1 is not a factor, but you can just divide by it, and when you divide by it, it won't go in exactly. It will give a remainder, and that is the remainder. So when you're doing your trial and error for the factor theorem and you put f of 1 in and it doesn't give you 0, what it's actually telling you is the remainder that you get when you divide by the factor x minus 1. Anyway, that's a little aside. They do ask that in AS questions. They sort of just say, oh, what's this remainder? And they use it as information in order to be able to solve some of those equations and stuff. So the remainder theorem is exactly the same, but it's just saying instead of if f of x equals 0, then, if f of a equals 0, then x minus a is a factor. Instead it's saying if you divide by x minus a, the remainder is f of a. And that's true in the factor theorem, because if you divide by the factor, the remainder will be 0. So, just quickly, find the remainder of this when it's divided by x minus 2. So they are not looking for you to do, the point is, not looking for you to do any long division here. As a lot of the kids, they read that and they go, oh, it's divided, I've got to do long division. And they spend hours struggling through it. The point is, because of this theorem, you don't have to do that. You just have to sub in a value for x and get the remainder. So what value of x are you subbing in?
I'm coming up with 11.
Oh, let's have a look. Did you sub 2 in though?
Again?
Did you sub 2 in?
Yeah, I sub -2 in.
Ah, okay. That's why. You need to sub 2 in. Remember the opposite sign.
Oh, bollocks. Yeah.
Yeah, that's why. But it's ideal, because if you made that mistake, then, you know, hopefully, this will stop, this is, you know, this is quite a whirlwind trip through this. You wouldn't normally do it all together. It would take numerous lessons to cover this at AS level. So yeah, I think the key that I'm always making is you're dividing by the opposite to the value that you put in.
So when you're trying to find the remainder, you're dividing by the opposite of the x, aren't you?
Yeah, you sub in.
But when you're trying to find but when you're trying to find the factor, you're subbing in the root.
Yes, yeah. Ultimately,
Yeah. Okay.
ultimately
Yeah,
the root. Yeah, the root. A root is when your function equals 0. So when you divide by something else, you're dividing by the remainder. Now, graphically, I don't know what that means. I don't think I don't think it has a meaning, does it? Because we're just doing an algebra.
Does it help you in any way to solve it afterwards? That's the question. Because if it doesn't, it's like, why?
Yeah, no, it doesn't. I don't actually know, apart from it being an algebraic, you know, bit of fun. I don't know why you would do it, apart from, you know, for the same reasons that we do division generally. You know, oh look, I need to divide this into this many things. Does it divide exactly, or do I get a remainder, and what is that remainder? So it's just that it's in an algebraic form. So we've got 13 x minus 2 left, which is a bit weird. So I'm afraid I do not know a real life. Okay, one use of it though is that it helps you to check that if you sub that in and you didn't get 0, you would know it does not divide exactly, and therefore you wouldn't beat yourself up about it when you were doing the long division.
Yeah, basically you could do this as a check before you did the long division, because if it doesn't divide in exactly, then it is not a factor.
Yeah, exactly. So, and I think some of the kids do this. I think they check to know what they should be expecting. However, generally, they're only give look, use the remainder theorem to check the remainder when using long division. So, I mean, I think that is really all it's for. If the remainder is correct, the quotient will be 2. Yeah, so that's it. However, more often than not, the long division they're given are used to factorise cubics, so they divide exactly normally. But they do like to give little questions like this. So these are basically applications of the factor theorem, completely contrived, but in an attempt to get people to apply them. So if x plus 2 is a factor of this, with unknowns a and b, we don't know what a and b are, and if the remainder of this, when you divide it by x minus 1, is minus 3, what are the values of a and b? Any ideas how you might start this? Have you ever seen anything like this before?
I'm just trying to rack my brains. It doesn't look too familiar, to be honest.
This is one of those things that I think we show the kids once and then they forget and they're completely flummoxed by. And they see the word division, they spend a lot of time doing a division, they're not really sure where they're headed. And it's just one of those little tricks. So, yeah, they do all this division, trying to do it into here, but it's got A's and B's. All you have to do is think, if this is f of x, we'll call this f of x, then if x plus 2 is a factor, what do I know about f of 2? What do I know about f of minus 2?
it equals 0.
Yeah. So what I do is I sub -2 into this side and I make it equal to 0. That gives me a little equation which, when sort of got everything across, I've got a little equation for A and B now. The other one is going to do the same sort of thing so that I'm going to end up with simultaneous equations that I can solve for A and B. So what am I going to do next? Bearing in mind that they've done f of -2 is 0. What else have I
Then
been told?
sub in, so you then basically just sub in +2, because that will give you a remainder. You then pull the same equation out using the remainder, which will then allow you to do your simultaneous equation.
Almost, except that we don't know the remainder for 2. What do we know the remainder for?
Oh, sorry, for -1.
Yeah. So if we sub in 1, the opposite one, we
Yeah.
know that f of 1 is -3. So if we sub in 1, we get this equation. So it's a really, what's the word I'm looking for? Obtuse way of testing this, because the kids get into exams and they maybe have seen this once, they have no idea. Because it's such a tiny topic, they don't really use the theorem much itself or think about what the theorem actually means. So yes, this is sort of the hardest, I think, to do with the remainder factor. So you get a simultaneous equation, but ultimately none of the maths here is anywhere beyond GCSE, and this is an AS level. It's just knowing what to do. I mean, all of these new words, and just it looks horrid, doesn't it? And then they're basically told, go on, find A and B. Well, obviously a lot of them will use trial and error again. But this is what they're expected to do. They can then solve those. A is 3 and B is -1. Any issues with that?
Once you get to those two bits, I mean, the simultaneous is easy enough.
Yeah.
It's just, it's just getting your head around the whole factors equaling 0 and like other things equaling remainders, and so yeah, you can use stuff through. So it's just the little clues and things like that, isn't it? But it's just
Yeah.
I kind of make it sense in my head, but not in voice. It's fine.
Yeah, no, it's earmarking those things for learners that if you see this, then what it's asking you to do is not divide in. It says that is saying if it's a factor of it, let's use the factor theorem. So we know that f of the opposite side of that will be 0. Couple that in. If it's remainder, then if I do f of 1, it will equal that. It's just really trying to make that clear. So in order to factorise a whole cubic, we use the factor theorem to find that first linear factor. We then okay, that's just saying that we use the opposite sign. We then use inspection or division to find the quadratic, and then we have to check whether the quadratic itself does it. I was just going to show you long division now, writing it on the screen. So to factorise this, actually I'm just going to see what's got on the next screen. Oh yeah, so I'm going to show you this one. So to factorise this, I need to find my first factor. So it's going to be something related to the 6. Let's try f of 1. I get 1 plus 2 minus 5. That's not going to work. Let's try f of -1. -1 plus 2 minus 5. Okay, that's not working again. Did I jump too quickly for this one? Plus 2. No. Oh, no, I've done that wrong, haven't I? That's why. Yay, that does work. So f of -1 equals 0. So I know that x minus 1 is a factor. So what I'm going to do, actually I'll do it in this a second. using the bus stop method of long division, I'm going to divide x minus 1 into my x cubed plus 2x squared minus 5x minus 6. Now, you can watch this and forget it for the rest of your life if you wish, and always just use inspection. Or to really get this, it does involve quite a bit of practice. So, just the same as any long division, I say, how many times does x go into x cubed? The kids find that really difficult to understand what I'm saying. They're sort of like, oh, there's 3 x's, so it goes in 3 times. No. What I really meant to say was, what multiplied by x gives me x cubed? So x times x squared, and I'm going to write it there above that x squared term. X times x squared gives me x cubed. Now I multiply this whole thing by that and write it underneath because that's sort of subtracted. So x times x squared is x cubed. Minus 1 times x squared is minus x squared. So it all lines up underneath. I subtract those. X cubed minus x cubed is nothing. 2x squared minus minus x squared is 3x squared. So that's basically my new quadratic, or this is like my new number. Sorry, my new number that I'm left with is basically the 3x squared and these bits. So I can bring all of that down, although I'm just going to do that thing. Well, I don't know, I'm doing that. Now I say to myself, I look here, this is my new thing that I'm dividing into, having taken off already x squareds of those. So x into 3x squared goes 3x times, so 3x times x, 3x squared. Now I do this multiplied by the whole factor, I get 3x times so 3x squared, 3x times x, minus 3x. There's nothing there. So 3x squared minus 3x squared goes minus 5x minus minus 3x is 8x. Bring down my minus 6. And I've got x into, okay, what have I done wrong? Oh, hang on. Minus 5 plus 3, Sarah. Okay, let's just go back here. 2 plus 1 is 3. Minus 5 plus 3 is minus 2. Okay.
5 plus 3 minus 2x, yeah.
Yeah. That's still not going to work, though. What have I done wrong? Haha. This is also a problem I find when teaching this, that I often make a mistake, and then the kids have lost interest. So let me just go back to, okay, well let's, because if I do this, you see, if I go x times into that is minus 2, it's not going to work because minus 2 times minus 1 is plus 2, and then I've got a remainder. I shouldn't have a remainder because this factorizes completely. Let me just check this is the right factor. Minus 1 plus 2 plus 5 minus 6. That is definitely 7 minus 7, so that was right. X into x cubed is x squared minus x squared. So x cubed minus x cubed goes 2x squared plus x squared is 3x squared. X times that is 3x minus 3x.
Hang on a sec. Just looking at here, your first one, when you subtracted x from 2x, x squared from 2x squared,
Yeah.
you've put your answer down as 3x squared.
Yeah,
Of
because
course,
I've
yes,
got
because you're subtracting
minus
minus x squared, aren't you? That's right, sorry.
Yeah, but something has definitely gone wrong here because I cannot factorize this completely. But it should definitely be able to. Okay, let me just finish it in case I've actually just been minus 5 plus 3 is minus 2. So x times minus 2, the minus 2 goes up there. So I've got minus 2x plus 2. So I think I have a remainder of 4. But that's not true because when I put that in, I don't get 2. Oh my goodness me! If I had finished f of 1, I can tell you now, I would have got 4 because what is the crucial error that I have made?
You haven't reversed your factor.
I have not! See, even, you know, that'd be a good one to do though, as a pretend example and be like, why does it not work?
Yeah.
Yeah. That is why. That would be 2. That would be 2. That would be 2. And that would be 2. 5 plus 2 is 4. No, it's not. Minus 5 plus 2. 3. Yay. Oh no. What am I doing? Oh no, plus 2x. Oh no, because I've got a plus 1 there. Right. That's how kids end up with that in their books, isn't it? Frustration. Sorry, that was really bad. Mustn't do that. Yes. So, what I proved is that when you divide by a divisor that's not a factor, you get the remainder.
Yeah.
But anyway, basically what you do is you just, hopefully you've got the idea that you divide in the first one, put it up there, multiply by and take it away. And that process would work.
Yes, you should have actually been dividing there by x minus 1 rather than x plus 1. Is that right?
No, I should have done x plus 1. I just put the plus in there, but I divided it all by x minus 1. So it did not work.
Right, yeah, absolutely. To be fair, watching you work through that process made more sense to me than just trying to do it via inspection, because I get really lost on the inspection thing.
Right, me too, which is why I get really lost on the inspection. I don't know quite why, because I get it, but I just can't see. My brain just doesn't work.
Yeah, I get lost with how far I've got. That's the thing. I start doing things twice and stuff like that. And
yeah.
Yeah.
This is why I encourage long division, because it gives a methodical way of doing it. So had I done
if you made a mistake on that, you know, a mistake like that with inspection, you'd never know where you got. You just have to scrub it and start again. Whereas at least you could see that you'd gone wrong somewhere.
Yes, and I checked all the division was correct. So because the division was correct, I did the division correctly, I was just dividing by the wrong thing. And I suppose that's important, isn't it? In terms of how do you look for mistakes, those are also things that kids need to know. I had come to the conclusion that my division was correct. I had done the method correctly. Thus, it must be that I had divided by the wrong thing. So then I could be like, oh, now I know. Yes, it's a bit annoying because you then it's better just to start again rather than try and correct it as you go through, I think. So here we go. X times x squared is x cubed. We write that in underneath, so I'll get x cubed plus x squared, 2x squared minus x squared is just x squared. Alright, 2x squared minus x squared is x squared. X into x squared is just x. Bring down the 5, minus 5x. So x times x is x squared, plus 1 times x is x. So minus 5 minus x is minus 6. Yay. Now we know that it's
Yay.
right. So x into minus 6x goes minus 6. As should have been the case because I had a 1. I knew it was going to be constant. So I can go minus 6x, minus 6, excellent, 0. Then I know it's correct. So my factorised form so far is x plus 1, x squared plus x. Oh gosh, sorry, my squared minus 6. So I just have to look at this bit now and factorise that. Any ideas?
Oh, it's going to be minus 6. It's going to be, I would have to guess that's plus x. So it's going to be negative 2, positive 3.
Yeah. So there we go. That is our fully factorised cubic. So I think ultimately there's nothing really difficult, but there are these key things that are so easy to cock up as you go through it. So there's, obviously there's just sometimes I just see this maths done incorrectly, so they think something's a factor when it's not. Then there's this point of switching the signs to get the factor. Then, if you do the long division, there's lots of little places that could go wrong, but equally same with inspection. Then a lot of them then forget to fully factorise. So they lose the last mark because it will generally say fully factorised. So these are often 6-mark questions and can get quite involved. So you guys are now going to have a go at these yourself. What's my 4:11? So have a go at these. I'm just going to click on, yeah, so this is our last thing, just you doing it. That was the whole of cubics that would normally spend a week on in an hour. So find your linear factor using the factor theorem. Use long division or inspection to find the quadratic. I mean, that's the big time-consuming bit. And then factorise the quadratic if that works. I've been really mean, actually, because these aren't just x cubed, they've got numbers of them. But do you feel confident that you can have a go at these now? Well,
I feel confident I can have a go. Don't feel confident I'll get it right. But...
Yeah, no, absolutely. I feel not so, yeah, no, that's a good distinction, isn't it? Not confident I can get it right, but I'm confident I could give it a go. And I think that's all that we want from the students, isn't it? Well, have a go. Ask me if you've got any questions. Second one's a bit off, sorry. The second one is really tricky, actually. So if you can do the first one, then that's great. I'm going to say that the second one is kind of harder than you would normally get.
Oh, that's not right. What have I gone wrong there?
Is that on the first one?
Yeah.
What did you get as your factor? Is it your linear factor?
Well, I stuck, well, I had a, oh, do you know, I think I've done exactly the same thing you did. Oh, you muppet, I thought I mustn't do the same thing, because I saw myself doing it, I thought, and then did exactly the same thing.
It seems to be done.
Oh, that is right. Yeah, I've gone, I managed to get it to factorise to 1. So
Yeah.
when I did the whole trying it out, I managed to get 1, as in positive 1, to give me 0.
Yes. Yeah.
So I thought, okay, it's 0. I must remember that it's the opposite thing, and then immediately wrote any factor, which should be next one.
Yeah, so you should have divided by x minus 1.
I should have been dividing by x minus 1.
Yeah.
I've currently got myself down to the bottom end. Well, I've got a remainder of like positive 8, positive 18, I think it is.
Right.
Sorry,
How did you find the long division?
22. The actual long division, sweet.
Right.
Sweet, had no dramas with that whatsoever.
Yeah, I love it, but lots of kids hate it.
Yeah, if I tried doing that as an inspection, I think I just like sat in the corner and cried.
How about you, Hugh? Have you done it using inspection, or have you tried long division?
I'm doing an inspection. I've realised I made a mistake first. I'm just redoing it.
Mm-hmm. The second one, I wouldn't bother trying. That is quite mean. Well, because, and I don't think they do this actually at AS. Where's my mouse? What's my mouse? No. Oh, that's because it's a thing. If this is a factor, 3x minus 1, you know, if we make that equal to 0, then what does x equal?
3x minus 1 is going to be 3.
No, it's going to be 1 over 3. Because when you make that equal to 0, the 1...
Oh, yes,
Yeah.
of course it is, yeah. Yeah.
Well, yeah, and we don't do non-integers. X is a third is horrible. So you could sub in x equals a third into there to demonstrate that it is a factor. Or you could do what I did, which was to divide it in. But it's a mean one. Because as you divide it in, if you look at this, actually, 3x minus 1 goes exactly, should just done it here, right? 3x minus 1 goes exactly into that first bit, what that's showing is factor. 3x into 3x cubed goes x squared times 3x times 3x squared is 3x cubed, minus 1 times x squared is minus 1. And minus 1x squared minus x squared is 0. Now if that happens, that's absolutely fine. It just shows that it does go into that bit exactly, and is thus a factor. Once you've got 0 there, what happens, you can either just go back up to here, or you can bring this down, because you're now going straight to this next bit.
X squared 4x.
Yeah, so it'll be 3x into 12x, just 4, so I'm going to put that over here. So there's no bits there. And then you check 3x times 4 is 12x, and times 4 is times 4, minus 4, and that's 0. So just doing the division shows that it is a factor. And to factorise it completely, you actually just have 3x minus 1 and x squared plus 4, which doesn't factorise anymore.
I thought when I originally saw as you're going through it, there wasn't like a 1 or 2x value. I thought, oh, it'll be difference to 2 squares, but of course it can't be because you've got a positive integer at the end.
Yeah. And a lot of kids will try to do that. They would write out, oh, look, that's the difference. Oh, yeah, because I need 3 brackets, I'll have to do that. But you don't always have to have 3 brackets. That one just doesn't have any real roots. Which means that as a graph, so it's cutting at a third, and that's the only place it's cutting. Because these would be the square root of minus 4. They're not real roots. That wouldn't work. So it's actually going to look, it's going to come through here and be like up there, no roots. Yeah, bit of a tricky one.
Yeah, sorry, so quick one on that. I'm just trying to remember what my graph theory was when you're doing quadratics. So I've got the right, you know, you've got that, obviously it comes up through a third, no dramas, and it dips back down again.
Yeah.
The vertex of that, is that, no, the bottom bit, is that still the vertex?
Yeah, so here we've got,
it goes back over.
Yeah, on a cubic we have 2. We've got a max and a min on this one.
Yeah, so the minimum vertex would be at positive 4, wouldn't it?
We don't know where those would be.
Oh, okay.
Based on this, we don't know that. After next webinar, you will be able to find them, because we will be doing calculus. You need calculus to be able to do that, and that's where the AS progresses onto, because you've got, it's fine when you're doing this one. So in fact, where did you find? What did you finish off this one? This first one?
Do you feel when I spotted my mistake, I didn't go back through it, I must admit.
Hugh, did you finish it?
Because we started chain, so.
Yeah.
No, I'm just getting some random numbers and I can't see where I've gone wrong, so I'm going to have a look at it again later.
Okay, I'll say the answer so that it's on the recording. It's x minus 1, it doesn't matter which order these are, 2x plus 1, and x minus 4. So that's what you should have got. Oh no, that's not right. Because minus 4 and minus 1 and 1 gives me plus 4. Hang on, I have done it
Yeah,
wrong.
that's right. Yeah, first time round, the A value is minus 2 and the C value is minus 4. I get a consistent B value.
I factorised my quadratic
And then the second.
incorrectly. Hang on. Yeah, maybe it doesn't. Maybe where's my pointer gone now? Sorry, I'm trying to find it. Fixing it. Where am I going? Okay. I've done that wrong, so that's not right. And I've not even checked that it might have put it out. So I'm trying to get the quadratic. When you divide in or use inspection, as your quadratic, you should get 2x squared minus 7x plus 4. So then I've just incorrectly, there's so many places you can go wrong, isn't there? So I've then gone, oh, 7, so I thought I'd gone, oh, minus 8 plus 1. Huh. But I didn't get my plus 4 there. So it's going to have to be, it doesn't factorise, does it? Excellent. So, yeah, I don't think that factorises either, does it? There's 2, so I'm going to work. So I'm only ever going to make it to 6, aren't I? It doesn't work with just sides either, does it? No. So, 9 plus 2, no, that one doesn't factorise either, so that's the answer if you do the inspection of the division. So there you go, I have fallen into all the typical pitfalls that the students face.
That was a very, very good demonstration for that. Thank you very much. That's good. We needed to see that happen so we could spot it before.
Exactly. Attempting to factorise things you can't factorise and managing it. And that's the thing, managing it and just thinking, great, I've done it, moving on. But yes, had this cut at 3 places like the previous slide, this one, that graph, so that cuts at minus 1, minus 3 and 2. Minus 1, minus 3 and 2, let's say. And it's positive, and I know it cuts at minus 6 down here. So it must go up there, down there, through there, and up there. So that shouldn't be pointing straight out. But these vertices here, now I don't know if the vertex is actually at the bottom or if it's, I won't know that yet. Those 2, I cannot find from any of this. I can only find by using calculus. So that is what we are going to be doing next time in the webinar on the 14th of October. We're going to be looking at calculus. Right, time for a break, I think, until 10 past 11. And then we
can do that. See you in a bit.
Yeah, and then we'll move on to circles. Okay.
Cool. and then the teacher.
Hello, are you guys back?
Hey there. I still can't get this damn cubic to factorise.
The quadratic doesn't factorise.
Well, no, I couldn't even get it to come out to the quadratic.
Well, maybe I've done it wrong.
Well, I say that. I ended up with something. It's just I keep getting. I mean, I've got as far as divide. I was trying to work out, trying to divide that cubic by x minus 1. Because I think that was because my factor was. I originally got a positive 1 to come out at 0, so I thought I'd go with the x minus 1.
Yeah, definitely.
So I'd end up with 2x squared, 7x on top. Because you multiply by that 7x, by that negative 1,
Oh, hang
I
on.
got to a point where I was...
Yeah, so you got 2x squared. So yeah, 2x comes out, so that's minus 2x squared there. Let me just delete this. When you take that away, minus 9 plus 2 is minus 7. So minus 7x squared. So then
7x squared. Bring down the plus. I think I might have seen where I've gone wrong actually.
Oh, I see. Yes. So that's minus.
Oh yeah, because you're then at negative 7x. Because when you take that through, so you're trying to write x minus 1 into a 7x squared plus 11x. So obviously you get x into x squared just comes up to 7x, which then comes back down as 7x squared. But then of course when you multiply that 7x through the negative 1, obviously you end up with negative 7x. You actually end up with plus 18x.
No, here there should be a minus 7x up here. Because 9...
Where did you get that from?
9 minus 2, sorry, minus 9 plus 2 is what we're basically doing.
Oh,
yeah, so that's minus 7. So then you get a plus 7, so 11 minus the plus 7 gives you a 4x.
Right. Of course, so when you bring the, that's when you, then when you bring the minus 7x back down, it comes as negative 7x, that cancels out. Of course, because I wasn't spotting that I got it the wrong way, because the x's still cancelled out. Or the 7x squared was still cancelled down as a negative.
Yeah.
So it's still working.
It's the same, yeah.
Right, that's why I was lost, because then you're coming down as subtracting positive 7x, that leaves you at plus, that's it, seen it. That leaves you at the 4x. And then, just divide straight in then, doesn't it?
Yeah. Yeah, but as you can see, I mean, I love this topic because it doesn't involve any actual thinking. It's just a procedure. I'm like, okay, put in different numbers, which one equals 0, great, reverse the sign, that's the factor, divide it in, follow this method, it all falls out. Beautiful. There's no great reason for it. And so the kids that want something that has a reason to it and don't like this methodical, boring process, hate it. Whereas I love it. So it's a really tricky topic to engage everyone in. Anyway, moving on to circles. Sorry, did you have anything more to say about cubics?
No, that's all right. I'm good with that. Now I've seen where I'm gone wrong, I'm a little bit happier. I was winding myself up because that silly little sign thing. Yeah. It'll
take a lot of practice, like it did when you first learned anything. It takes a lot of practice. Right, circles. Before now, really, the kids just know, you say, what do you know about circles? Pi r squared is one of the first thing they say. Oh, no. The first thing they say is they're round. Yeah. So they're just hilarious. So, I mean, generally they'll go, I get them like mini whiteboards and like, write down everything you know about circles. And you just kind of get, they're round, pi r squared, 2 pi r. You might get a few people like labeling them up, radius and diameter. You might get some really, circle theorems. Unlikely, though. However, the fact is that, like any graphs that we draw, a circle is a type of graph. And so we can have an equation for it in order to draw the graph. Which is a bit of that's a really new concept to them. So they have to be able to grasp that concept and then use it to find what the equations are. So I sort of generally start down this route. Okay, we've got a circle and I've drawn it onto an axis, and the centre of the circle is at the origin, 0, 0. And this has got a radius of 1. So all the way down, that would be 1, that would be -1, that would be -1. Now, that is also 1 because the radius is just from anywhere, so from the origin to anywhere on the circumference. Now, if that is my radius 1, if I have a point xy on the circle, then I can say, okay, well, I've actually now got a little triangle made up of an x distance along to there, and y distance is the height. Now, bearing in mind what I know about Pythagoras' theorem, what can you say? Can you come up with a little equation linking these numbers?
Yeah, I mean, basically, you go x squared plus y squared equals 1.
Yeah.
Or so the square root of 1.
Yeah. No, technically 1 squared, actually. But it is still 1.
Yeah.
Yeah, so by Pythagoras' theorem, we can come up with x squared plus y squared equals 1. That is true, because this is just a point, a generic point xy. That is true for any point xy, because that's how we like coordinates, on this circle. So if I put in any values of x and y that make this true, make it equal to 1, I will basically have plotted this circle. So that is the equation for this circle. X squared plus y squared equals 1. Now, if I try various points, we can see that 1, 0, I don't know why that's there, that's really annoying. Oh, that's the distance sign, okay, that's fine. I thought I was labeling that as a 1. We can see that 1, 0 lies on the circle anyway. We can sub it in, and we've got 1 squared plus 0 is 1. Excellent. Satisfies that equation, so it must lie on the circle. Equally the same is true for 0, 1 and everything else. So we substitute in, check that it equals 1, and it does. So if we are ever given a question which says, show that the point satisfies the equation, we have to do this little thing where we say left-hand side, put it into the left-hand side, so say, oh yes, that equals 1, which is the right-hand side. Okay, so that's how we show if something satisfies an equation. The kids get a bit confused because they kind of just go, yeah, 1 squared plus 0 squared is 1. But you've got to kind of demonstrate, oh yes, but that is that side and I was using this side. So that's how you show an equation is satisfied by a point. However, if we put in 0.5, 0.5, which would be about there, I suppose, we put it in the left-hand side, we get half, which does not equal 1, because it does not, so it does not equal the right-hand side. So we know that the point 0.5, 0.5 is not on this circle. It's inside the circle. Because it is less than 1, we know it must lie inside the circle. So often they're given points when they've got their equation of a circle. They're given some points and asked, does it lie inside the circle, on the circle, or outside the circle? If the number is less than this number, then it must be inside. If it's bigger, then it'll be outside. So now let's go to a more generic one. This one, instead of having a radius of 1, we're going to say that the radius is r. So now, using Pythagoras' theorem again, what would be the equation we can put together involving x, y, and r?
X squared plus y squared equals r squared.
Yeah. So for a circle of any size that's around the origin, the equation for that circle is going to be x squared plus y squared equals r squared. So no matter how big or small I made the radius, that would always be the equation of the circle. So that helps them to, again, identify sort of where we're coming from. But circles aren't always just round the origin. If this whole thing was moved so that it's actually now got a centre AB, then if we now think about this, what is this distance here? This bit here, between here and here, right?
Still. Whereas this in terms of the Pythag theorem?
Yeah, well, in terms of these letters, if I go down to here, so that's A, isn't it? And that's X. So yeah, what is that distance here? So, you do know?
X minus A? X
Yeah,
minus A?
exactly, yeah. Because X is actually the distance all the way from the origin to there. So this bit here is X minus A. And equally, what's the height?
X minus Y, isn't it?
Oh no, here we go. We've got
Y minus B.
Yeah, y minus b, good. Y minus b. So now, and then we'll say that the radius is still r. Now, using Pythagoras, what would be the equation of this circle?
Brackets X minus A brackets squared plus brackets Y minus B brackets squared equals R squared.
Yeah, Hugh, is that what you were going to say?
Oh, sorry, Hugh.
Yeah, that's what I was going to say. I've just been writing it down, so I'm trying to get it written down before I say anything.
Have you done this before?
Yeah. Just sort of refreshing the memory because it's all starting to come back.
Yeah. Mark, have you done this before?
About 30 seconds ago.
Yeah, so circles is a bit of a weird, random little topic that just crops up in C1 and then is never really seen again. So again, the students find it difficult to remember. They remember the stuff they do again and again, but it gets used a lot. But this doesn't really get used very much. So yes, using Pythagoras as before, there is our formula. That is the equation for any circle. So, okay, let me delete my things. So, bearing in mind that if you see this, like this, we could have jumped straight to this by just knowing, as we do, the centre and the radius. But again, here we are, it is again the opposite sign. So if the centre is AB, the equation will be x minus A all squared plus the y minus the b all squared. So those two bits are the X and Y coordinates of the centre, and then it's the radius squared, and they forget that. They forget that this was derived from Pythagoras. They need to always do that because they end up just writing the radius, or they end up square rooting it because they get, you know, it backwards in their heads. So they've really got to think about where this came from and try and remember it. Another way of doing it, and it depends on the order in which I've taught things. If I've been doing transformations first, which I sometimes do, I will say, well, hang on, if I translate something, when I move it to the right, then the centre moves, but it's the reverse sign. So I've moved along by A and up by B. So my translation means that I change my x becomes now x minus A, and my y becomes y minus B, and that's how you get it. But because we haven't been doing transformations, that makes less sense. And I think the Pythagoras route is, it's, you know, to be honest, you could start your whole AS teaching, if you ever do it, with circles, because Pythagoras is something that they have known for years, and, you know, it's sort of a bit of a quirky topic. It doesn't require much else. So, I mean, that is it. The equation of a circle, knowing the centre and the radius, is that, and we leave it like that. Okay, and I've written to do circles and translations activity sheet because I think I did this at the ISW last year, not as a webinar. However, I have uploaded that to Student Central. So you can see that. That's a good one that goes between translations and circles and how we relate the two things. So, if we know the centre and the radius, we can just write down the equation. So I use the formula, x minus a squared, my a is 4, y minus b, my b is minus 3, and my radius is 5. So I've just got x minus 4 squared plus y, and it's minus minus, so it'll be plus 3 squared, it's 5 squared. So that is the equation of my circle. So if you're told any centre and radius, you can just come up with the equation of the circle. They then say, does the point lie on, inside, or outside the circle? So we take the left-hand side, sub in the coordinates, 2 minus 4 squared plus 1 plus 3 squared is 20. It's less than 25, so it must be inside. Yeah, exactly, inside the circle. Okay. Any questions about that? Any of that?
That whole thing about the left-hand side business made far more sense when you just did that. I was a little bit confused what you were doing before, but that now makes sense.
Yeah, and I'm sorry, it's because of also the way that the click-throughs, the top bit disappeared, and I was just left at that bit at the bottom, so I need to adjust that slide anyway. So yes, that's what we do. Because what I get though, the problem is that if you don't do it left and right hand side, what happens is the kids try to do both bits together. So they've written this, they've written down the right hand side of their thing, subbing in the left, so they've like used that whole thing. And that's just not true. So then they're like, oh, 20, and I see this written a lot because they've worked down both sides, 20 equals 25, and then they've put, no, that's wrong, so it must be less. I don't want to see that. I want to see you do the left-hand side and then you do the right-hand side, not, you know, kind of making it fit after. It's just bad math, that's all, bad grammar. So there is this. They might be asked a little question about it and asked to sketch it. The sketching circles, that's so mean. It's really tricky to sketch a circle. Now, the opposite way around, if you are given a long-winded version of this, so it's not in this form, and you need to find the centre and radius. So like this. This is why I said to you, it would be good if you could practice completing the square. So at the moment, faced with something like this, hopefully the students would think, hang on, there's an x squared and a y squared. I think this is a circle. But it doesn't look quite like a circle should be. So I need to get it to look like that. So I need to group my x squareds together, my x's together. So those are my x's. I normally write them next to each other first. Can you remember how to complete the square?
Yeah, it's it'd be half. So you have x, so obviously it's x, then half the minus 6x would be halved.
Yeah.
So it'd be minus. So it'd be x minus 3x in both. That'll be in the brackets with the square sign. Then you have to multiply that out, and then whatever you need to get rid of the plus bit at the end. So it could be I think if that's -6, that'd be 9 minus 9. I think it'll be. Oh, it might be plus 9, but I think it's 9, -9. So that'd be
Right.
bracket x minus 3 squared minus 9, I think.
Exactly, yeah. I was gonna say. One of the things the kids forget, yeah, one of the things the kids forget is, like you were saying, they put an x in there, and then they think, oh, it's -9, so I need to add it, or whatever. You are always taking it off, because it's an extra, so you're always taking that off. I don't know why I'm writing this, because it does actually do this for me. So yeah, you halve that. That's what it would be if you multiplied it out. So you get x squared minus 6x plus 9. So we need to get rid of that 9, so we take that away. Okay, Hugh, can you do the y's for me, please?
Y minus 2 in brackets squared, take 16. Oh, sorry, take 4.
Oh yeah,
that.
good. Yeah,
That's the wrong number.
Easy to fall into that, especially when you're not writing it down necessarily. Yeah, so we do both of those. Don't forget this -12 here, which is really easily done. Now, in order, oh, that jumped too far. In order to get it to look like the circle, what we want to do is take all these numbers over to the other side. So we've got -9 and -4 and a -12. So we've got a -25, which would be 25 on the other side, which is fortunate because you wouldn't want to have a negative radius. That would just be weird. So collecting it all together, that is what we've got. If we compare that with the equation, annoyingly I was going to ask you this, but it's the centre is going to be, always remember the opposite signs of these. So the centre is 3, 2, and the radius is the square root of that, because r squared equals that. So r itself is 5. So in fact, was that the same centre? Was that exactly the same one as we had here? No, that's 4 minus. So if faced with this sort of thing, you have to group the x's together, group the y's together, complete the square, put all the numbers on the other side, then compare it to the equation of a circle. Remember, the centre is the opposite signs of those, and the radius squared is that number. So the radius is square root of it. So that is what that says there. That's exactly what it said. So have a go yourself at doing these. So group the x's, group the y's, complete the square, and then compare. Actually, I'll write down the equation of a circle because it's still very new to me. Now, a lot of the kids forget this is a plus here. Because of the minus in the brackets, they often write a minus between. They have again forgotten that it derives from Pythagoras and is a squared plus b squared equals c squared. Yeah, but when you've done both of those. So Hugh, what did you get for the first one?
First one, I ended up getting centre at 2, -4, radius of 4.
Good, yeah. Because, I mean, really, I think all we're testing is quadratic completing the square, which you would have had to have reminded the kids of, again, at AS level, because lots of them will not actually ever even have seen it at GCSE. And then just, know this information about the equation and just make sure those are the right way round. Okay. Mark, did you manage to complete that one?
Yeah, I mean, it went slightly weird, but I suppose it's still right. I've got A and B is -3 and 0.5 positive with a radius of 3.
Yeah, it's just, kids don't like weird numbers.
Yeah, it's just weird because I ended up, after going through the whole thing, I ended up with -9 as my last bit. But and obviously, when so something squared is, you can't be -9.
Yeah.
So I just took it as a 9.
Oh, okay. Now that's because, I'll show you, when you complete the square here, even though that's a positive,
Yeah.
you've got to take it away. Yeah, and then when it goes over the other side, it becomes a positive 9. Like that.
Right.
Yeah, it's
Yeah.
because of the way that it's written, so that the r squared is on that side, it then sorts itself out, basically. So that it will always
Yeah.
be that the radius is on that side of the equation. But yeah, it's a bit of a weird one, isn't it? With having a
Yeah.
half. But that's just,
Yeah.
that's the coordinate.
Yeah. So basically, I think if I got this right, then if the number's on one side, as in not the numbers outside the brackets on one side don't cancel out to 0, then they just carry over to the other side as the opposite sign, basically, don't they?
Yeah, well, they shouldn't be 0 anyway, because that's going to be, the square root of them is going to be the radius. Hopefully,
Yeah.
there'll be a square number, but they're not always that kind. In fact, you just then generally leave it as a surd, so it'd be like root 40 or something, if, if it's not something
Yeah.
that is very nice. Right, now let's look at what happens when we have a line meeting a circle. So there is the line y equals x plus 1. This is the circle of x plus 2 squared plus y minus 1 squared. So its centre is minus 2, 1. And it's got a radius of 2, as you can see. Now this actually says it meets at the points minus 2, minus 1 and 0, 1. But often this would be the sort of question. It would say, where do these two graphs meet? Do they meet? Okay. Again, if the line cuts the circle, it will satisfy the equation of the line and the circle when you put the points in, as you'd expect. So here they're just substituting them in. That would be a very simplistic question. I mean, they might just say, oh yeah, let's sub it in. Oh yes, great. It works in both of them, they must therefore meet. More often than not, they want you to work out where they meet rather than telling you. So, to do that, we would need to solve the equations simultaneously. So to find the coordinates of the points where the line y equals 1, x plus 1 cuts this circle, this is a sort of simultaneous equation that gets the kids a little bit confused because they're used to often using elimination rather than using substitution. So you'd want to go back and make sure that you've done quite a lot of sort of quadratics with substitution and stuff. So if we simply replace y with x plus 1 here, then we've got two brackets. Actually, this one, because of the plus 1 minus 1, that just gives us 0 anyway. So we've just got x squared. But we need to multiply this one out. So we multiply out the x plus 2, because you've got to get everything out, collect it all on one side, and then try and solve it. And that's what everyone forgets. They forget that in order to be able to solve any sort of quadratic, must equal 0 on this side. You see it done time and time again. I spent a whole lesson where I couldn't figure out where I'd done something wrong, and it's because I've left a number over here. So again, we all do it. So you multiply that out, bring the 4 over, that actually cancels out, and you're left with 2x squared plus 4x equals 0. Now we can factorise this. And again, by the time they get to this, the students seem to have forgotten factorising all of a sudden and start dividing by things and lose a solution. So factorising, common factor is 2x. Oh, they've taken out. They've just checked that this definitely has real roots and they can factorise. I think it's fairly obvious anyway, but that's how you can check. So taking out 2x, we're left with x plus 2. So either 2x equals 0, so x is 0 is one of the coordinates, or x is minus 2. Those are the two x coordinates where the line cuts the circle. Always got to remember to find the y coordinates too. Often the kids stop here and forget that. And always put it into the linear one. You get them kind of like putting it into here and then having to rearrange. And they can simply go, okay, so y is 0 plus 1, so y is 1. And -2, so y is -1. So those are our two coordinates, which definitely agree with them. Now, if the line doesn't cut the circle, then it's just floating nearby. And that would mean there's no solutions, and you will get a quadratic you can't solve. So you can still sub in just the same. When you collect it all together, this can't be factorised. And if you use the discriminant, b squared minus 4ac, it will come out negative, showing you that there aren't actually any real roots, and therefore there are no solutions. So often they want to say demonstrate that there is no points of intersection. So you go through all this to get a quadratic to which you can apply b squared minus 4ac. By showing that that's negative, that shows there are no points of intersection. So if it's positive, then there are 2 real roots. If it's negative, there are no real roots, so no points of intersection. What if it's 0? What does that mean? Any idea, Hugh, in terms of a line and a circle?
Ah, did it just mean context 1? Sorry.
Yeah, no, that's it. And what do we call it? When
It's just a tangent, isn't it?
Yes. So it is a tangent. That is what it says. The line just touches the circle. It's then a tangent. The discriminant equals 0. Oh, I thought I had a picture, but I don't. Sorry. Yeah, so those are your 3 possibilities. It's always good to get down to your quadratic and check it with the b squared minus 4ac, so you're not spending ages trying to figure it out. But you'd get a repeated root, so when you did your quadratic factorising, you'd find that they were both the same. So those are your 3 possibilities, basically. So either doesn't intersect and your discriminant's less than 0, it has 2 points and so it's positive, or it just touches and so it's equal to 0. Just the same really as when you're just trying to solve a quadratic and you say, oh, if it's negative there are no real roots, so it's all above the axis. If there's 2, then it cuts to the axis twice. If it's not, it's a tangent to the axis. Does that make sense?
Yes.
Any questions? Because you're going to do it now. So, so you've got your circle. You don't have to feel that don't feel that you have to complete the square to do it, but it can be. Well, it's up to you. It doesn't really matter. Either way, you're going to sub in your line. So either you sub it in, I would just sub it in without bothering to complete the square. Sub in your line, collect it all together as one quadratic, and then use the discriminant and figure out how many points of intersection, and then find those points of intersection. So put your hands up when you finish that one. Those two.
Oh. No.
The second one that's
No, still.
what did you do? Is it the first one or the second one that's troubling you?
I haven't survived the first one yet.
Oh, okay. What did you do?
Well, I did the complete in the square.
Oh, right.
So I ended up with x minus 1 squared plus x minus 2 squared minus 5 equals 0. Substituted in the 2x for the y. So I had x minus 1 squared plus 2x minus 2 squared minus 5. Broke up, expanding out both those brackets, made it into one formula, which gave me 5x squared minus 6x plus 5 equals 0. Then tried doing something funky with the discriminant and come up with 64, and I have no fucking idea what that means whatsoever.
That means it's positive and it's got 2 points of intersection.
Oh,
So
okay.
the discriminant, the number of the discriminant means nothing in itself. Okay, it's just that
Oh,
it's
right, okay.
positive. Yeah, it's just that it's positive, and therefore there are 2 points of intersection. So to find those, you then
Right.
need to factorise the quadratic you've got left. So you should hopefully have ended up with 5x squared minus 10x.
I've got 6. Where did I get 6 from?
That I don't know, because
Yeah,
I did
I've got that.
Yeah.
Can I just check my answer? Because I'm getting out at 0, 9 and 2, 5.
Oh, I've got 0, 0 and 2, 4. Let's keep
I've done something wrong then.
So at what point is the question?
I should double check. So I got 5x squared take 10x equals 0.
Yeah.
So factorise 5x and x minus 2.
Yeah, that's it.
So x equals 2.
Yeah. Yep. And
so
then
y equals
yeah, you've set them into this
2
one.
times 0.
That one instead of that one.
That's right.
That's all. That's
Yeah,
all.
right,
Okay.
my bad.
Oh, sorry, my doorbell.
Yeah.
Yeah. Sorry, I think the patient's just there. I keep going with the second one. I will be back in a second.
Yeah.
Yeah, I got to that point and then I just lost it.
Yeah. Nah, fair one. I'm just getting there. I'll factorise this bastard now. That's negative 10.
Sorry, just taking a pulse from next door. So you, that's fine. You just put yours in the wrong one.
Yeah.
I think Mark.
So I found out why I didn't get the negative 10x. Right, when I was expanding out 2x minus 2, I only took out one negative 4x. I didn't bring out the other one.
Right.
So I was shy. That's why I had negative 6. I'm desperately now trying to remember how to factorise a quadratic when it's got an alpha value.
Yeah, so all you do, because this one doesn't have another number, all you've got to do is look for the common factor in both of those.
Okay, so take the 5x out.
It's just a 5x, yeah. And the kids forget that, because they're so used to a 3-term quadratic, they forget that it's actually simpler with a 2-term.
That's better.
So I will leave the other one, I think, for you guys to try in your own time, because that, I'm afraid, is more difficult, because it's even more multiplying out lots of squared brackets and stuff. I think the key also is, yeah, I guess the good decision is, do you want to complete the square on it or not? I don't think it makes a difference. It's just still a lot of algebraic messing about. But that is the method. I think you all follow the method precisely. It's just a matter of this, really, just, you know.
Yeah, so, sorry, last quick one. So if I factorise out that 5x squared minus 10x,
Yes.
so I've effectively got 5x, open brackets, minus 2x.
No, x
plus
minus 2.
Oh, x minus 2, right.
Yeah, because 5x times x is 5x squared. And 5x times minus 2 is minus 10x.
Yeah.
There you go. So it's like this one here. And then it's just each bit 5x is 0, so x 0, or x minus 2 is 0, so 2.
I'll have to look into doing that some more. Yeah.
Yeah.
More practice with that.
Yeah.
So it's trying to find the time to practice this stuff on top of doing everything else.
Yes. So there's a self-study next week, but I'll upload it. I'll upload it after this, and so you could, if you're free now, you can just keep going into that. So then you can hopefully apply what we've done today. I think I've made the self-studies this year a lot more just practicing this rather than developing a deeper understanding in a more, rather than it being abstract, it is just do these questions. Okay, so, and that means that it's easier for me to do the answers also to send to you because they have actual answers, whereas last year it was all a bit of a, there were various different ways you could do things, and I kind of because we're talking about theory a lot more in the webinars, the self-studies, I've made more practical maths. Anyway, I'll click through this one so that it's there. There's a little bit more. We've got what, 10 more minutes? Yeah, 10 more minutes. But I'm guessing that you're probably getting to that point where you might need a break. Then, on top of this sort of bit about solving, in fact, Hugh, did you manage to do the previous one or not? Did you do that one there?
I'm just working on it just now. I've got down to the solution where I've got 5, then x takes 3 squared equals 0 as my full factorization. I'm just doing the b take 4ac to find out how many intercepts it's got.
Okay. Well, because
Have a look there.
The reason I'm saying this in a really unprofessional manner is that I'm dying for the loo. So I was just going to say, actually, can I leave you to do this one while I pop to the loo? What did you say? 5x minus 3. Is that going to be enough?
Yeah, I've done it all out.
Oh, right, so you finished that one, in fact.
I've got to go to the loo, make sure that I've done it right.
Okay. Well, do you want me to show you the answer on the screen, and Mark, you can work your way through it? There you go.
Yeah, please.
There you go. I'll put it there, then you can see what
I'm not exactly finished.
Right, it's on the screen.
I've got.
Okay, yeah, well, brilliant. Well done. I'll be back in a second. Right. So, down here. So you've got to about here, haven't you? And have you managed to factorize that? Yes, did I did my b squared minus 4ac and thought, oh, it's a tangent, but it looks so weird because when you look at this one, you think, oh, well, how am I going to get the same bracket? And I actually factorized that into 5x minus 15 and x minus 3, but then obviously when you do it, it does come out. So Hugh, did you manage to get down to the bottom?
Yeah, what I was doing was working out how many roots it was when you asked.
Right, right.
Because I got to it, then where you've got the x minus 3,
yeah.
I just written it down as x minus 3 squared. So I knew that x was 3.
Right.
So I'm going to find out how many tangents, I'll see how many intercepts it was before I found out why.
Yeah. Yeah, and I did too. Yeah.
At that point, so that's why I thought I'd check.
Yeah, it's a good way to check, isn't it? Yeah, so Mark, if you at some time, I mean, there's a lot of algebra going on here, that's all. And it's just a case of being very precise and careful, which, as you've seen,
that certainly following it through would make more sense than trying to work through how I work through the other one.
Yeah, yeah, I think that actually when you're doing this, it's not worth bothering with the extra step of completing the square, because yeah, you still at some point have to do some multiplying out of quadratics.
Mm.
So you may as well just forget about the completing the square.
Yeah.
So there are 3 circle theorems that are relevant to properties of circle that may be needed to solve problems. The first one, let's see if this works. Let me, oh, maybe I've clicked through. Here we go. The tangent to a circle is perpendicular to the radius at the point of contact. And there's a nice little applet Java where it used to basically, you could get it to go all the way round, and it shows that it's always, the tangent is always at 90 degrees to it. That one actually doesn't actually look like it is 90 degrees, but it should be. So that's the first rule they have to learn, which helps, because you might be told, this is where we get back into coordinate geometry and straight lines, because you might be told the radius, or sorry, you might be given the equation of the circle, in which case, and the point here where the tangent meets it, in which case you could find the equation of this line and be asked to find the equation of the tangent and know that that is perpendicular, and thus that you have to use sort of m1 times m2 equals -1. So this is where the circle stuff suddenly brings in a lot of the straight line stuff. So often they basically encourage drawing diagrams, little sketches to help yourself. And I mean, occasionally they've thrown a real hardball where we had one where, you know, it's really difficult to figure out what was going on. And I couldn't figure it out algebraically and ended up drawing myself a graph. This is just a C1 paper. You know, the kids would come out going, oh, well, that is an impossible question. And I sort of had to draw myself this little sketch of it in order to solve it, and then realise what I need to do. So find the equation of the tangent is a very typical sort of question. You've got the 2 points from the centre to there, and because of that, you know that's the radius, because the tangent, because of that fact that a tangent is perpendicular to the radius. So you can find the equation of the straight line, the radius that goes between 2, 3, and 5, 7. So we find the equation of that line using all of that, which is, oh, come on, we just find the gradient. Y equals -3/4 x plus 43/4. Well, that's clever. Right. That is the equation of the radius using just our straight line geometry, that is kind of the top of GCSE and the beginning of AS. And therefore, the tangent is supposed to be perpendicular to that, so the perpendicular gradient. Now, we didn't actually need to know the whole equation of the radius, really. All we needed to know was the gradient of the radius. And then we can find the perpendicular gradient. What will be the gradient that's perpendicular to this one, -3/4? Can you remember how to find a perpendicular gradient? Oh no, hang on. Sorry, apologies, I'll pay attention. Right, that was the gradient of our radius. So they've done exactly what I was going to do. They found the equation of the radius there. Then they have made it into the perpendicular gradient by doing y -1 over that one. So the -3/4, sorry, is the perpendicular gradient. So that is that gradient. And thus, when they put that point in, this is the equation of the tangent, which would make much more sense. That's now -3/4. So this is just, again, as everything is, it's just extending the stuff that they know about circles. It's just in straight line geometry. but using this knowledge about circles. And they do the same again. I won't do this one. Okay, so this is the one where you know the circle theorem, that if they cut two tangents from the same point cut at, they are of equal length where they cut, where they are a tangent to the circle, they are the same length. So if we join up with the radius, they want to know the length of the tangent. So again, you can find the equation, you find where those meet. So this is quite an involved question. You can use Pythagoras by making a right angled triangle, and then you can find that length there. So CP is root 20, based on the length between those points, using that's the distance formula. And then because you've got the distance of that, you've got the 3, you can actually then find the length AP in just the same way. So that was all using distance formulas and lengths, which we haven't done so much. Anyway, I'm skipping through all this because we have come to the end. So there are some exercises here. So finding the equation of the tangent. We've given the centre, and well, you can work out the centre based on this equation. You've got a point, so you find the gradient of the normal radius, and then find the perpendicular one, and that's the same. So this is just going through all that very quickly. Another property. So this is at the end of this, you'll be able to see it. There's just a lot of properties. There's 3 properties. There was the fact that the tangent is perpendicular to the radius. Then the perpendicular from the centre to a chord. So this a chord, it's just a straight line that joins 2 bits. The radius coming out to the edge of the circle will bisect that. Again, this ties in with sort of what they knew about circle theorems, and it helps them to work out various bits, like they can work out the length of the chord or all sorts of things. So that's it, they want an equation of this chord. So I don't have time to go through all of this. I'm just going to go through to the next property. The third property is the one that the angle in a semicircle is a right angle. So when you draw a diameter across, the angle that makes when you draw a triangle inside it is always going to be 90 degrees no matter where it sits. As you can see there. So that can be useful again to find the various things related to the circle. So the end of this topic, basically, that we haven't really had time to go through, but it's all here on the slides, is all about, we've learned about the circles, which in itself is quite simple, isn't it? It's just knowing the equation. And then it brings circle theorems and coordinate geometry into it. So they end up with something like this. This would be quite a mean one, but this could be an exam question. Got a circle, centre's P, and it's told you 3 points that the circle goes through. It's also told you the midpoint of AB and D. So calculate the coordinates of D. Because we've got the 2 points A and B, we can use our coordinate geometry to find the length of them, and we're told that, we can use those 2 points to find the midpoint of them, and with the midpoint, that's D. We can find the gradient using the gradient formula. The equation of the perpendicular bisector of AB is just going through the process. You find that gradient, you find the normal gradient to it, and you take that point D that you've used. So using part 1 and 2, you can find the equation of PD. And then that line and this other perpendicular the bisector meet at P. So you just go through that same process again to find that perpendicular bisector. You have the simultaneous equations, you can find P. Then you know the centre, and you can calculate the length PD and find the equation of the circle. It's a lot of work. Probably a 9 or 10 mark question at least. But it's actually all just coordinate geometry, which is the top of the circle falls under this. So we don't have time to do those, but I've put all of these up on Student Centre as well. And I will put the self-study up. In fact, it says it on Student Centre, which suggests that I have already done it. So the self-study, in fact, just to check, it looks like this. So you've got using the factor theorem to find the other bits of the polynomials, factorising them and sketching the curves, some bits to do with remainders, sketching some circles, finding the centres, showing that's a tangent, find the points of intersection, sketching that one. So the bits with the properties of circles, I haven't tested you on that in here anyway. So that's why I kind of skipped through it. But otherwise, this self-study basically tests exactly what we have done today. So please work through it and email me when you've done it. I'm aiming to create answers for them and send you the answers. Rather than what's happened before is you having to scan them in or whatever and send me your answers. But I just haven't got that. But I will try. Anyway, next webinar. First of all, sorry, are there any questions about circles?
Nothing that I don't think I can answer without going back over the slides and stuff. The stuff towards the end there lost me a little bit because we were going quite quick. But I'll go back over it slow time and see what I can manage. And if we have any issues, I'll give you a shout.
I mean, that was it. The bits that are at the end are kind of extra. They are in AS, but it brings in all the linear, the coordinate geometry stuff, and you'd need to brush up on all of that, really, before doing it, I think, which is why I haven't gone into it.
Before I can do it, to be fair.
Yeah. So, but everything that we did before then, up to the sort of intersections and stuff, that is kind of was the main thing that I wanted to put on there. I just thought that I should put the extra bits on there. How about you, Hugh? Was that a reminder mainly?
Yeah, a little bit mind-blowing towards the end, but going through it again, I'm sure I can make more sense of it. I do have one question that I can ask offline. It's just,
okay.
I was teaching a group something that, and one of them said to me, I just want to double check that I'm thinking correctly before I tell them yes or no.
Okay, let me stop the recording anyway.